mean, it's just each axis goes to 90 degrees, and then goes to negative 90 degrees, and then goes home.
Oh.
So it's just moving the base.
Yeah, I had it in sequential mode. I want to do it all in one.
Now, do you have buttons to push for just manual move?
Huh?
Is that what you're doing now, just pushing the manual move buttons? Do you
Well, I
let
have to
the move just
specify
move it
them.
while it's pressed?
Huh?
Do you have any buttons to run it like a pendant or anything?
No,
No.
we don't have. You would have to actually go and input a position. But
You can move it.
You can move it.
He's got it where you can just click move on each individual axis, and he has it overall.
Yeah, this is just to show step by step.
Yeah. This is what it is.
They're all going in line.
Yeah, there's
Lines
just...
at the same time.
Now, did you calculate it to keep that one vertical, or
Well,
just
Yeah.
the way you'd chosen it?
Well, it's actually going negative 90 and positive 90.
I know it is, but
Sorry.
keeping the vertical on.
yeah, the reason we did that is we used the home positions based on the,
Okay.
yeah, which
You mean instead of going downwards, or...
yeah, because
It was just a particular, I mean, you didn't really decide on a frame of reference, so all the gear ratios are just positive.
Yeah, they used to the LED.
Do you have the final scaling in degrees for each axis, or some encoder counts?
it's
Yeah.
degrees correct. You can do both, right? You can
Yeah,
choose.
so, I mean,
And you have document how much encoder counts
Yes.
for.
yeah, we have.
Did you calculate that, or determine it empirical by measuring?
We try to measure when. So we first found the gear ratios in different documentation, and we just Tomas's created a VI that will calculate.
So it's based off the gear ratio.
Yeah, it's based on gear ratio, and then we try to come back here and measure the actual physical angle, but we didn't
We got too much
actually
error.
find a way of measuring that properly.
Yeah.
So we just
It's
measured the
it's
base
better
one.
like the gear ratio.
so it's just like...
I mean, the one thing we did do is
5, 6, and then...
these are 90 degrees away. We centered it, told it to go 90 degrees, and got from here to another one.
But for the other ones, it's more complicated, just because of the shapes.
Okay, let's start with home position. Do you have in your document how somebody sets a home position or a sequence of operation if you start up the robot? Let's say you come
there's
in
just
and you
a-
turn everything on, and
Yeah.
this thing
He has a.
is falling over in some, or was turned off in a position that is not.
There's a button specific on his VI. That's
Yeah,
home.
if you look at the software, it's just...
No matter what position it starts at. It'll go to home.
So there's like a control for each axis. We can kill or send home or start move separately, and then these are like for all of them. So if you hit home on this, everything will go
Yeah,
home.
everything on.
And then there's...
Can you describe the home sequence, what physically is going to happen? If I home axis, how does it do it? What's it reading? What's it set?
Yeah, so it's based on the potentiometer value, which were, for the most part, based on the markings
Now,
on
is
the
it
robot.
is it going to the home, then moving back to the first index pulse on the encoder, or is it just
We didn't
using
use index because we needed to break out more cards to actually use the digital signals, right?
Yeah.
You
Or
guys
that
use
signal more
You using variable resistors?
as the home position.
They're built into the motors.
Okay.
They have an encoder in the top.
Okay. Okay.
Well, the indexes are wired through the cable, but you just didn't wire them through.
We have them.
No.
They're there to
They're actually
use. We
connected.
just didn't use them.
Yeah,
Yeah, RBI.
they're all the way wired,
Okay.
so it can be used, you know.
So they're wired through to those breakout boards?
Yep.
Yeah.
So why would you need more breakout boards to put them
No.
in?
No,
No.
I was wrong.
yeah.
Yeah.
There was two other ones that were for digital
Okay.
that I was thinking about. That's
And
okay.
how accurate are the potentiometers? I know things, it's just a variable resistor,
What
so
did you
it's.
say earlier?
Well, we know 5
20,
volts.
25 millivolts?
Oh, the reading?
Yeah.
How many encoder counts? Can you tell how accurate they are?
Yeah, I mean,
Can
we
you
did
send
something,
it to
we
a-
don't have anything like official, but we were doing that at one point, and I remember the count is being like, I don't know, in the tens of encoder counts
10 and
per
15,
millivolt,
yeah. So, I mean, the actual percentage is like 0.17%. Pretty accurate.
We set up software limits.
When you
So-
start doing kinematics, you have to, rather than percent, you have to kind of relate it to end effector position or what it means.
We set software limits. So yeah,
On the potentiometer.
no, actually on the encoder.
Okay, so you're using the potentiometer at home,
Oh, that's
the
it.
encoders, and then you're using the encoder position signal for the limits.
Yes.
Okay. So you're not using the potentiometer for any limit purposes,
No.
No, just for the.
but you're bringing it into A to D channel on the card.
The pot? Yeah.
Yes, sir.
There's
So
a-
you're moving to a home position, and you're servoing it to that resistance value or voltage value?
Yeah, just the slow
Basically.
speed, right?
What's controlling the accuracy of that? Is it drift in that voltage of the potentiometer with temperature? Is it the control accuracy of just getting right back to the same number? What is limiting the accuracy on?
Well, I mean, there's an algorithm in one of the papers that we reference on how to really do it accurately, and that's what we would have liked to do. But right now,
That's where we use the index pulse. That's what most machines do.
yeah, and also, I mean, it's pretty clever. It estimates from. You have to calibrate each potentiometer.
Did you reference that
Yeah.
article?
Yes, in fact, it's
It's-
actually included on the CD in the
Yeah,
article.
because that's a good thing to.
Yeah, right, because the repeatability is not, super accurate.
For
like,
the potentiometer.
yeah, so if you eyeball it, yeah, it looks like it always gets the same position. But if you look at the readings, it's not as accurate as like an encoder can be.
Yeah.
But yeah, the paper goes through how you take a potentiometer reading, get an estimated encoder reading, and go from that to get a really accurate find home. But we just didn't have time to get that.
Okay, on the control points, when you do the servoing, so you're actually servoing against the potentiometer value when you do that. Okay,
Yeah.
and all other moves you're using position feedback from the encoder.
Yes.
So you have two different ways you're doing that.
Yes.
And so the accuracy is, you come back usually to the same voltage value if you're 10 counts off on encoder typically. How many, and you look at the voltage number on the potentiometer, you're always coming back to the same potentiometer number, or is that difference in voltage that you're coming back to consistent with the encoder count distance and just the accuracy of your servo? Let me give you an example. Okay, you move to a home position, you get close to whatever it is, voltage on the resistor. Okay, so you know the conversion between the voltage and the coder counts. So there are two approaches. You can try to keep servoing, which takes a lot of time to get it right in there. Or you can say, okay, I'm 50 millivolts low. Therefore, when I preset my encoder, I should preset it this many counts low. Are you going to that specification?
Yeah, we didn't think of it that way, but that would certainly like increase the accuracy.
I think it would. Yeah, I think it would. Okay.
And just because we chose to use the potentiometer for the home location, that could really help us like.
Because I mean, on a lot of the robotic stuff, if they're going to use, some of them use resolvers. They're kind of like absolute position devices. They're not incremental. And sometimes they'll use that approach rather than try to control it. You just stop it near it, and you know the sensitivity on that position readout, and you use that difference to go either more or less on your encoder counts. So, okay, so 10 encoder counts. The motors are typically 90 degrees. How many encoder counts is that?
For us,
Wait, man.
Isn't it? Well, it's 1,000 encoder
Yeah.
counts per rotation, right? So,
We have the
in most of the axes.
yeah, so,
What's the conversion from encoder counts to degrees?
it varies per motor.
yeah, it's
Let's
different.
take the base motor.
It's written in the report.
It is,
okay.
Yeah.
Yeah, we did
I don't know the
that.
number off the top.
We did the conversion.
I don't know if we wrote that, but I mean, it's
Give me a guess. Is it
We have-
10,000, 100,000, 1,000?
I mean, it depends on the gear ratio. But
Yeah, exactly.
Yeah,
I can't say offhand, and it's not something we did.
We didn't memorize them by heart, but we did
What's the
explain.
gear ratio? Isn't it 50 to 1 or is it more?
This is right there, 62.61 to 1.
Okay, so approximately 60 to 1, and it's, how many
Right.
line encoders? Is it 1,000 line, 4,000
Thousand.
quadrature
Thousand.
per rotation?
Yeah.
Yes, sir.
Okay, so you've got 60 to 1. So then you got 60
Quarter.
rotations of the
So
motor
15,000?
per 60 degrees.
Wouldn't that be 15,000? Wouldn't that be 15,000?
For what, for 90 degrees?
Oh, for 90 degrees, I'm saying.
Yeah.
Yeah, so that makes sense, what he was saying too.
Yeah. So 10 counts out of that. Of course, you measured 0.17% you mentioned on
Yeah, those.
during the final presentation.